In 1991, the Navy ordered 620 aircraft that would revolutionize carrier aviation. The stealth attack jet promised capabilities no enemy could counter. 4 years later, the program was dead, costing taxpayers $5 billion with not a single aircraft delivered. The A-12 Avenger II represented technology so advanced that even America's defense industry couldn't build it. But the real story isn't about failure. It's about ambition that exceeded engineering reality by a decade. Welcome to Flight Deck. Today we're examining the A-12 Avenger II program, why the Pentagon canceled the most expensive aircraft development in history, and how this flying wing's revolutionary design actually worked too well on paper while proving impossible in practice. The A-12's shape shocked everyone who saw the classified design. Picture a smooth triangular flying wing with no vertical surfaces, no protruding cockpit, nothing breaking the radar-evading contours. The aircraft looked like someone had flattened a stealth fighter into a pure wing shape. Every angle was calculated for minimal radar return. Every surface blended seamlessly into the next. The design represented the ultimate expression of stealth technology. And that's exactly what made it unbuildable with 1990s manufacturing. Understanding why requires looking at what the Navy needed. Carrier-based attack aircraft face unique challenges that land-based planes never encounter. They must survive catapult launches that subject airframes to brutal acceleration. They need reinforced landing gear and arresting hooks for carrier recoveries that slam aircraft onto deck at controlled crash velocities. Saltwater exposure corrodes everything. Weight restrictions become critical because carriers can only launch aircraft below specific limits. Now add stealth requirements on top of carrier operations. Stealth demands smooth surfaces without gaps or irregularities. But carrier aircraft need robust, maintainable structures that can handle extreme stress. Stealth requires exotic composite materials, but carrier operations favor tough, proven materials that won't fail catastrophically. These contradictory requirements created engineering challenges that nobody had solved before. The A-12 design team at General Dynamics and McDonnell Douglas promised to deliver everything simultaneously. Their flying wing configuration would provide stealth superior to the F-117. The weapons bays would carry massive payloads internally. The range would exceed any carrier aircraft in service. On paper, the specifications looked revolutionary. In practice, building it required technologies that didn't exist yet. The composite material challenges destroyed the program before it ever flew. The A-12's flying wing design demanded large composite structures that could handle carrier operation stress loads. Traditional aluminum construction was too heavy and didn't provide the smooth surfaces stealth required. Composites promised lightweight and smooth surfaces, but working with them at the required scale proved nearly impossible. Composite materials behave differently than metal. They don't bend and flex predictably. They don't fail with obvious warning signs. They require precise temperature and pressure during curing. Any variation in the manufacturing process creates weak spots that can fail catastrophically under stress. Now imagine building an entire aircraft from composites, not just small components. Imagine ensuring every square foot meets structural requirements while maintaining the precise surface contours that stealth demands. The manufacturing equipment didn't exist to build A-12 components at required tolerances. The team needed massive autoclaves, essentially giant ovens that cure composite parts under controlled heat and pressure. But the autoclaves, large enough to handle A-12 wing sections, hadn't been built yet. The contractors tried bonding smaller sections together, but the joints created structural weak points and broke stealth surface continuity. Every solution created new problems. Quality control became a nightmare. X-ray inspection revealed voids and delaminations throughout composite structures. Parts that looked perfect externally harbored internal flaws that made them unusable. The rejection rate for major components exceeded 50%. Contractors scrapped parts that cost millions to manufacture because they couldn't meet specifications. The program burned through money-producing aircraft sections that would never fly. Weight growth crushed the design. The A-12 was supposed to weigh 80,000 pounds maximum for carrier operations. As engineers struggled with composite manufacturing, they added reinforcement and heavier materials to ensure the aircraft wouldn't fail. The weight climbed steadily, 85,000 pounds, then 90,000, approaching 100,000 pounds. At those weights, the A-12 couldn't operate from carriers effectively. The entire purpose of the aircraft was being compromised by engineering reality. The cost overruns reflected these technical struggles. The original contract specified $4.8 billion for development and initial production. When composite manufacturing proved far more difficult than anticipated, costs exploded. The contractors needed more time, more equipment, more engineering resources. Every month of delay added tens of millions in costs. Pentagon leadership faced an increasingly difficult decision: continue funding a program that might never produce operational aircraft, or cancel and accept the $5 billion loss. The A-12 had consumed resources that could fund other programs. The Navy desperately needed replacement aircraft for aging A-6 intruders. Defense Secretary Dick Cheney made the cancellation decision in January 1991. The announcement shocked the defense industry. Never before had the Pentagon terminated a program this large after investing this much money. Cheney cited cost overruns, schedule delays, and technical problems that showed no signs of resolution. He acknowledged the $5 billion loss, but argued that continuing would waste even more taxpayer money on an aircraft that might never work. The contractors fought the cancellation through years of litigation. General Dynamics and McDonnell Douglas claimed the Navy changed requirements and caused the problems. The government argued the contractors failed to deliver promised capabilities. The legal battle lasted longer than the actual development program, with courts ultimately ruling mostly in the government's favor. The technology gap that killed the A-12 seems almost quaint today. Modern aircraft routinely use composite structures that would have been impossible in 1990. The F-35 features composite wings, fuselage sections, and control surfaces throughout. The B-2 Spirit bomber eventually solved many of the flying wing manufacturing challenges that defeated the A-12. Manufacturing technology advanced to where the A-12's requirements became achievable, just not when the program needed them. Autoclave technology improved dramatically through the 1990s and 2000s. Manufacturers built larger curing ovens capable of handling major aircraft sections. They developed better process controls, ensuring consistent results. The composite manufacturing that seemed impossible for the A-12 became routine for next-generation aircraft. Computer modeling advanced to where engineers could predict composite behavior accurately. In 1990, designing composite structures involved extensive physical testing and trial-and-error refinement. Modern software simulates how composites will perform under stress, where failures might occur. This capability allows engineers to optimize designs before manufacturing begins, reducing the costly iteration that plagued the A-12. The program's lessons shaped how the Pentagon approached advanced aircraft development afterward. The F-22 and F-35 programs incorporated technology maturation requirements, forcing contractors to prove critical capabilities before full-scale development began. The painful A-12 experience taught the defense acquisition system that ambitious requirements must align with demonstrated technology readiness. Flying wing designs never disappeared despite the A-12 failure. The B-21 Raider bomber uses refined flying wing configuration, incorporating lessons from both the B-2 and A-12 programs. The design team understood manufacturing challenges and planned accordingly. They used proven composite techniques rather than pushing technological boundaries. The B-21 represents what the A-12 should have been: evolutionary advancement rather than revolutionary gamble. The Navy eventually received its stealth carrier aircraft through different paths. The FA-18EF Super Hornet incorporated some stealth features while using conventional construction. The F-35C provided true stealth capability using technologies that matured after the A-12 cancellation. These programs delivered operational aircraft rather than expensive promises. The A-12's shape remained classified for years after cancellation. Eventually, photos leaked showing the distinctive triangular form. Aviation enthusiasts debated whether the design could have worked with more time and money. Defense analysts argued the program never should have started given technology immaturity. The truth lies between these extremes. The A-12's design wasn't fundamentally flawed. The physics worked, the stealth shaping was sound, but the gap between theoretical performance and buildable hardware exceeded what 1990s technology could bridge. The contractors genuinely believed they could solve the manufacturing challenges. They weren't lying about capability, they were wrong about difficulty and timeline. This distinction matters for understanding why ambitious defense programs fail. Sometimes contractors deliberately mislead about capability to win contracts. But often, engineers sincerely believe they can solve technical problems, only to discover the challenges exceed their estimates. The A-12 fell into this second category. The technology simply wasn't ready. So why did the Pentagon say no to the secret fighter too advanced to build? Because the A-12 Avenger II promised revolutionary capability using technology that didn't exist yet. Because composite manufacturing in 1990 couldn't produce the massive structures required for a carrier-based flying wing. Because weight growth and cost overruns revealed engineering problems that showed no signs of resolution. The A-12 represents the danger of reaching too far ahead of available technology. The design was brilliant, the requirements made sense, the contractors were competent, but the gap between what the program needed and what manufacturing technology could deliver proved insurmountable. 20 years later, many of the A-12's technologies became routine. But in 1991, they were science fiction masquerading as engineering plans. What surprised you most about the A-12 program? The composite manufacturing challenges, the massive cost overruns, or how the technology eventually succeeded in later aircraft? Let me know in the comments. If you want more deep dives into military aviation programs and defense acquisition realities, subscribe to Flight Deck. Until next time, remember that sometimes the most advanced designs fail not because they're wrong, but because they're early.